Hello, guys, and happy Thursday. I hope everybody enjoyed Greg's P1 lesson yesterday. If you're hoping to see him today, don't worry, he will be back. So if you're wondering who am I, my name is Joshua Beck. I am from Clayton, North Carolina. I teach at Clayton High School. It's just outside of Raleigh. So Greg and I are going to be co-teaching over the next couple of weeks here. So you'll be seeing a lot of us both. Our goal during this process is to really do as much as we can to help you guys prepare for the upcoming exam, to kind of finish out your course. It's an unusual time, so we're going to try some unorthodox methods here and see what we can do to help you guys out. So Greg and I are both real excited about it. Yesterday, he left you with a problem. If you didn't get a chance to watch yesterday's lesson, that's okay. I've put the problem up here on the screen. Greg was talking about angular velocity. So when things move, a lot of times we talk about their translational motion as it moves from one point in space to another, but they can also move around a particular axis where the location of the object stays the same, but it's rotating around this point. So he was talking a little bit about rotational motion. We're going to continue talking about that. But he gave us this problem at the end of class to try and create some velocity and position versus time graphs for an object that's rotating. So before we dive into that, I actually want to review a little bit about what equilibrium means. So I want you to see if you can answer this in your own room or wherever you're watching this video right now. How would you know if something was in equilibrium? I want you to think about this for just a second. There's probably a lot of different answers out there. Some common ones that we see, sometimes we'll see a student will say, well, if it's not moving, then it's going to be in equilibrium. So other students might say, I think it can be in equilibrium even if it is moving. So I want you to take a moment and look at these two statements and decide if you think that student A is correct, either partially or fully correct, or are they completely off base? And then do the same for student B. Do you think that student B is completely correct, partially correct, or totally off base? See, the interesting thing about what student A says, if it's not moving, then it's in equilibrium, is while they are partially correct, it's not a completely correct answer. They're leaving some things out because, as student B says, it can be in equilibrium even if it is moving. But what student B said isn't necessarily always correct either, because there are plenty of scenarios where something's moving and not in equilibrium. See, both students are missing kind of the key. The key to deciding if something's in equilibrium is less about if it's moving or not and more about its acceleration. So if an object is in equilibrium, then we are going to expect to see that it has an acceleration of 0. Now, yesterday, Greg talked about rotational motion. He talked about angular velocity and angular acceleration. So we're going to be focusing today on our angular accelerations, but they follow the same rules as our linear accelerations. See, student A was really talking about what we call static equilibrium. Static equilibrium means that the object is just stationary. So if it's in static equilibrium, we'd say the velocity is 0. And as long as the acceleration is 0, meaning that velocity doesn't change, then it'll be in equilibrium. Student B is talking about a possible case of equilibrium that we call dynamic equilibrium. Still an acceleration of 0. The only difference is in this particular case, the velocity is not equal to 0. But whatever that velocity is, it's going to be constant. It's not going to change. So how does this relate to the question from yesterday? Well, the question yesterday looked at an object that is going to be rotating. So we're not talking about linear velocity, we're talking about angular velocity, but there's a really important clue in this. It tells us in this part B that the acceleration is reduced to 0. Now, the acceleration that we're talking about here is going to be an angular acceleration like Greg talked about yesterday. So if the acceleration is 0, then that means this object is in equilibrium. Even though it's moving, it's still in equilibrium. So if we go to sketch a graph, I'm actually going to start with the velocity graph. We're told that this has an initial angular velocity of omega d. It's not a numerical value, but it is our starting point. It represents a numerical value. Now, if the acceleration is 0, then that means this velocity is going to be constant. So as time passes, you're going to find that we have a horizontal line here that's going to indicate that we have a constant velocity. Now, how could I sort of justify this horizontal line? Well, we have to think about this graph, and what does the graph show us? If we look at the y-axis on this graph, it's angular velocity. So if I look at this change in angular velocity, and I divide it by the change in time, what I'm doing is finding the slope of this graph, and that's going to give me my angular acceleration. Well, we know that the acceleration is 0, and if I look at this line, I see that the slope is 0. Now, how does this correspond to a position time graph? Well, let's start at a certain position. Now, again, this is not moving with a linear displacement, but it is an angular displacement. It's going around and around and around and around. So it does have a different position. So as time passes, that position is going to increase bit by bit by bit at a constant rate because it's got a constant velocity. So we'll end up with a straight line like this. Now, with all of our position time graphs, the slope here is going to be the change in position over the change in time. In this case, it's a change in angular position or an angular displacement over time, and that's going to give us our angular velocity. That's not 0, but it is constant. So the slope here is going to equal that constant velocity that we were given in the problem. Now, the second part of this, we made one change. There's still a really important clue that we need to continue using, which is that the acceleration is 0. The only thing that changed is our initial velocity. So where our first graph, we had our initial velocity here as omega d, now our initial velocity is going to be twice that. So let me see if I can switch colors. And we're going to go up to a point up here to omega d. Now, because it's in equilibrium, it's going to behave the same way. That velocity is going to be constant throughout. This line is a slope of 0 because the acceleration is 0. And then over here on this position time graph, we started out, I'll go in red, we started out with this displacement, except now it's moving at twice the speed. So we should expect to see in that first period of time, we should go twice as far. That next period of time, twice as far. And our graph should go up like this. Still a straight line because it's a uniform velocity, but much steeper. And so the slope of that line, instead of being omega, it's going to be 2 omega. So this slope will have twice the value. Now that's just sort of a recap of the question that Greg left you with yesterday. If you didn't get a chance to watch it live, that's okay. With any of these videos, if you miss one, you can always go back and watch them on recording. And yesterday, Greg gave you a way to kind of reach out to him and ask questions with @Jacobs Physics. I was trying to answer some questions as well, and we'll kind of go back and forth. But up in the top left corner here, you should be able to see a way that you can reach out to me as well if you have any questions. So let's jump into today's lesson. Today's lesson, we're going to try and figure out what actually caused that rotation. Greg had a pulley yesterday with a string draped over it. And when that string pulled on this, it caused a rotation. So what that string was doing is it was actually creating a torque. A torque is just something that's going to produce, or at least attempt to produce, a rotation. So a force can create a torque if it's applied in a particular manner. There's two sort of requirements that have to be met. The first one is that this force has to be applied some distance away from the point of rotation. So this pulley yesterday in his example had a point of rotation right here, right in the center. Well, you can see that this force right here is going to be applied at some distance away from that. So I can mark this out and say that we are some distance r away from that point of rotation. If I were to apply that force right here at the center of the pulley, that wouldn't have caused any rotation at all. So in order to create this rotation, in order to generate this torque, we have to apply that force offset a little bit. Now, our second requirement in order for a force to create this torque is it needs to be perpendicular, or at least a portion of it has to be perpendicular to that r vector. So we've offset our force with some r vector right here. And you can see the way that I have this drawn, this is at 90 degrees. So every bit of this force is perpendicular to that r vector. So every bit of this force is generating a torque. If I would have pulled at an angle like this, Well, only some of that is actually perpendicular to that r vector. Only the component that's in this direction here would actually be generating torque. If I were to pull all the way over here like this, then this is parallel to that r vector, and absolutely none of that force would create any torque. And you can see visually, if I pulled the string like this, that's not going to make this pulley rotate. So with all that, we end up with an equation for torque. This little symbol down here, this is on your reference sheet that you'll have on the exam. So you've got this little symbol here. This is just a Greek letter, tau. It's a lowercase tau. It stands for torque. And you can see that there are two components to calculating torque, R and F. R is this value that, whoops. R is going to be that value that we just labeled right here. That's going to be the distance away from that point of rotation. And then F is going to be the size of the force. This component here, this sine theta component, that's really only going to be used if you're pulling at some angle. So let's look at a couple examples here. I don't want you to draw this, okay? Don't take the time to draw this. This is just gonna be 2 quick hits, and then we'll get into some actual visual examples you can draw. Here I've got a beam of some sort, it's got a hinge. This could be, imagine kind of an aerial view looking down on a doorway. I want you to decide which of these following would create the largest torque. I've got FA and I have FB. Now torque is going to be calculated with R times F. So both of these forces are exactly the same. So we just have to compare the R values. The R value here is going to be much smaller than the R value here. So even though these are both the same size forces, RB is going to be a much bigger value, so it's actually going to give us more torque. So in this case, this force is going to give us more torque. Let's try another example. Again, don't write this one down, just take a look. Which of these two forces, they're both being applied at the same point, which of these two would create the largest torque? In this case, both forces are exactly the same, and both R values are the same because they're both being applied over here, except for we've got one important difference, which is one of them is applied at a totally different angle. FB is applied at a 90-degree angle, so every bit of FB is going to go towards the torque. FA is off at an angle right here, this angle theta. If we were to take the sine of that angle and multiply it by F, what we're going to do is we're going to find this component, which is just the component that's perpendicular to that R value. So you can see that this component of force A is much smaller than this component, or than this FB. So in this case, FA is not actually going to produce as much torque. So once again, FB is going to be the larger torque. So now I do want you to draw something. We're going to dive into this today. So let's get you to start drawing this. We've got a fulcrum sitting on a table, and then I've got a meter stick. Okay, I'm going to be switching over to a video in just a second, so I'll give you a moment to draw this setup. I will be switching between looking at this setup on the PowerPoint as well as on the video, and I'll be notating on both, but your drawing will match up with both, whether you're looking at the illustration here or the actual video. So here it is, not quite as crisp and clean, but hopefully you can see everything. I've got this meter stick, it's balanced in the middle. And then I've got this force sensor down here, which is just reading the value that this force probe is picking up. So if I push on this, you can see that value changes. Nothing attached to it right now, so it's giving us a value of 0. So if we look in this meter stick, I want to ask a couple questions. First one is, how do I know that this meter stick is in equilibrium? Now remember, it's tempting. You want to say things like, well, it's not moving, so that's why it's in equilibrium. But remember, the key to equilibrium is going to be analyzing the acceleration. So what we really want to say is, how do I know this is in equilibrium? Well, I know it's in equilibrium because it's not accelerating. Now there's two forms of acceleration. There's a linear acceleration, A, And we know that A is going to equal 0. What that means is this meter stick is not accelerating down towards the table. It's not getting accelerated off the table. It's not getting accelerated this way or some combination. But we also know that there's an angular acceleration, and that has to be 0 as well. So that means that this beam or this meter stick is not accelerating around with any sort of form of rotation either. So that angular acceleration is also going to be 0. So what I want you to do is I want you to label the forces that are currently acting on this meter stick. Now, how do we do this? Well, just put yourself in the position of the meter stick and ask, is there anything pushing on you or pulling on you? So if you're this little meter stick, you are in the Earth's gravitational field. So when we draw our forces, let's start with this one here. We'll call this mg. That's the force of gravity pushing down on this meter stick. The m that I would use would be the mass of the meter stick. Now, if that was the only force, what would this object be doing? Now, don't tell me it would be moving. I know it'd be moving, but we can be more clear than that. If this was the only force on this object, not only would it be moving, but it would be accelerating, which is a special type of movement. So it'd be accelerating down towards the table, would be in free fall. Clearly, that's not the case. So there has to be some other force in play. The other force is going to be the force of this fulcrum. I'll call this a normal force, that solid contact pushing up against it. So we've got this normal force holding it like this. Now, are either of these forces creating a torque? Remember, a torque is something that is going to cause a rotation. Either of these capable of causing a rotation? If you think back to your equation for torque, it's R times F. And what did R stand for? R was a distance away from this point of rotation. Well, if I try and measure the distance away from this point of rotation, the R value for both of these is going to be 0. So the torque, if I try to calculate it from either of these forces, is going to be 0. So neither of these forces is capable of producing a torque based on where they're currently located. Now, what I'm going to do is I'm going to add something to this. I'm going to take this. This is a 200-gram mass. So we'll call that 0.2 kilograms. And I'm going to hook this over on the edge right here. Got a little rubber band ready for it. I'm going to hook this on the edge. Okay. So before I do that, I want you to go ahead and add that to your diagram. Go some distance over here. Downward force of gravity. And I'm going to call this big M G. Little m we'll call the meter stick. Big M we'll call this extra mass. Now, if this has a mass of 0.2 kilograms, when I multiply that by G, this is going to end up giving me a weight of about 2 newtons. Now, if I hang this mass off of here, is that force capable of producing a torque? Is that one capable of producing a torque? Well, remember, torque is R times F. We know it's a force, so the question is it being applied at some distance away from point of rotation? And the answer is absolutely. Now we can look at this and see what that R value is. On the meter stick, it says 20 centimeters, but that's not going to be my R value. My R value is the distance from this point of rotation. This fulcrum is put at 50. So this would be 10, 20, 30 centimeters or 0.3 meters. That's my R value. So is this capable of producing a torque? Well, let's see. Torque is R times F. In this case, my R value is 0.3 meters. My F value is going to be 2 newtons. So absolutely, this is going to give me 0.6 Newton meters worth of torque. So if I hook this up, what's it going to do? We say that a torque is something that will create a rotation. So if I let this thing go, of course, it's going to make it rotate. Okay, so that extra force will create a torque that will make this thing rotate. Now, that's not what we want to happen. Okay, I don't want this to rotate. What I want is I want it to stay in equilibrium. So I'm going to pose a question for you that we're going to work our way through today. The question is, what can you do, or what can I do, since you're not here, what can I do to put this back in equilibrium while in the horizontal position? Okay, so I want you to think, what's something that I could do to put this back into a horizontal position. Now there are several options here, right? Several different options. We'll look at a couple of them and kind of compare and contrast what's similar and what's different about them. So one option, probably the most straightforward one, is this little force or this little weight is pulling down on the meter stick. So if I want to counteract what it's doing, why don't I just push up on the meter stick? So if I just simply push up right here, well, then I can keep this thing in equilibrium. Okay, this is probably the most straightforward method. So let's get our force sensor out here, start getting some values. Let's see exactly what this is going to take. Now, while I'm setting this up, you can probably guess what force this is going to be. Go ahead and hook this thing on here. This little force sensor. I don't know if you can see that. It says 1.97. We'll call that about 2 newtons. Probably not really all that surprising. The force, this going down was 2 newtons. So probably not a surprise that a 2 Newton upward force will put this thing back in equilibrium. Okay, so let's keep note of this. That was a 2 Newton force. It is also applied at an R of 0.3 meters. Okay, and let's go ahead and add that to your diagram. I'm going to switch back to the illustrated version, but go ahead and add that to your diagram. So we're back on our diagram. So the question is, why did this put the meter stick back in equilibrium? Well, let's start by, I'm going to put the original forces back on here. This is what your diagram should look like. We've already labeled the forces. We had little mg. We had normal force, that's the fulcrum pushing up. Then we added this. This was big mg. That was the hanging mass. And then we just applied this additional force right here. Okay, so that's what your diagram should look like. So the question is, why did that put it back in equilibrium? Well, remember, equilibrium means a couple things. Equilibrium means that the system is not accelerating. And when we first hung the mass on there, that system accelerated, but it accelerated with a rotational acceleration or an angular acceleration. It started to rotate around that pivot point. It didn't just all fall to the table. One side fell towards the table, the other side moved up. So this meter stick was actually rotating. So in order to get it into equilibrium, what I really need to do is get that angular acceleration back to 0. Well, what caused that angular acceleration was a torque. So if I had an unbalanced torque, I need to rebalance that torque. I need to make sure that all of these torques are going to be balanced. So let's check the math on this. We already calculated the torque from mg, from big mg. Okay, so the torque from big mg was going to be 0.6 Newton meters. Okay, we already calculated this. Now the torque from this one here was 0 because it's at an R value of 0. The torque from this one is 0. It's at an R value of 0. So what we need to do is we need to balance out that torque with this one here. Well, the first torque, we calculated a value, but we didn't really give it a direction. It's tempting to say that the torque from this big mg is down. But remember, that part of the meter stick moved down and this part of the meter stick moved up. So what that meter stick actually did is it started to rotate like this. Now, it obviously didn't go that far because the table stopped it, but it's trying to rotate this way. So this original mg tried to create a rotation that was in this direction. Now I can't define that as up or down or right or left because it's all of them depending on which part of the meter stick we're talking about. So instead, the way that we're going to define that is we are going to define that torque as a counterclockwise torque because the direction of rotation that it tries to create is in the counterclockwise direction. Now the torque from this one, this added force, you can see that that's going to push this meter stick up. But when the meter stick gets pushed up on that end, this end's actually going to go down. So that's actually going to try and make this rotate this way. So we would actually call that a clockwise torque. So in order to get our torques balanced, to get our net torque equal to 0, what I need to do is I need to create a clockwise torque that is also equal to 0.6 Newton meters. I don't know if you remember what this force was when we just had it on the video screen. This force was 2 newtons. And the R value, where that force was applied, was 0.3 meters. So this is also 0.6 Newton meters, exactly what we need. So the reason why this balanced this meter stick is less about the fact that it was the same size force as big MG, and it's more about the fact that it created the same torque that big MG did, but in the opposite direction. See, we balanced the torques. Now, what can we find out about the normal force in this case? See, equilibrium is not just balancing the torques, it's also what we're familiar with from our previous units. It's also balancing just the forces themselves. So let me re-notate, let me get all our forces back on here. MG of the meter stick didn't create any torque because it's right at the rotation point. Fn didn't create any torque, so it's right at the rotation point. Big MG absolutely created torque. This applied force created the opposite torque to balance it. But how about if we just look at our forces in general? If I want my forces to be balanced, then I need my upward forces, that's going to be my applied force, and the normal force, to equal my downward forces, big MG, little mg. Now my upward force was 2 newtons. I don't know my normal force. Big MG was 2 newtons, and I don't know the meter stick. But what I can see here is that my normal force in this particular case is going to be equal to mg of the meter stick. Go ahead and keep track of that. We're going to come back to it a little bit later when we compare a second method. So method 2, what's this going to look like? I asked you guys to come up with a way that you could balance this system. I'm going to go back to the video. One way that we could balance it is we applied this upward force over here. Now, is it possible that I could balance this some other way? Well, of course. There's actually lots of ways that I could balance this. So remember, the whole reason why we needed to do anything is because this big mg created a torque. There was a force that was applied, offset from that point of rotation, and it created this counterclockwise torque. Now, F1 was an upward force, which created a clockwise torque that could balance it out. Now, is it possible that we could create a clockwise torque by applying a force over on the right side? Could I apply a force over here and still create a clockwise torque? Well, sure. But I can't do it with an upward force, because if I apply an upward force over here, that's going to create more counterclockwise torque, which is going to add to what this hanging mass is trying to do. So what I need to do on the other side is I need to actually apply a downward force. Over here on the left, an upward force created that rotation. On the right, I'm going to need a downward force to create that rotation. Again, those would be working together. Both of those are creating a clockwise torque that can balance out the counterclockwise torque from this hanging mass. So let's bring our force sensor over here. Let's go ahead and push down on this. And we'll get this thing set, and we can see what this value is going to be. So right here, we can see that this is roughly 2 newtons again. Now it has a different sign on it. The other one was a +2. That's because I was pulling up. This is a -2. It's pushing down. That's just the way that the force sensor is set. You can actually just reverse the direction. Whoops, I didn't mean to do that. I zeroed it with something on there. There we go. There we go. I just reversed the direction. So now it's a positive value. The positive and negative is just used to define our directions. Okay. So for this one, we're actually going to draw a new diagram. Okay, we have a little bit different setup. I have different forces in different locations. So let's go ahead and actually get set up with a new diagram. So take a minute and I want you to label the forces that are now currently acting on this. Here's your setup. Okay. Now on your diagram, let's go ahead and label. I'm going to switch over to the illustrated version. We still have mg. This is the meter stick. I still have Fn. This is from the fulcrum. Now that value may or may not be the same. We'll check that out in just a second. Last time that normal force was just equal to mg. So we'll check that out in a second. I still have big mg over here. That's the 2 newtons. Except for now, I have another force over here. This is my applied force. Last time I had it here, don't have that one anymore. So it's a little bit different free body diagram. We've got some forces in slightly different places. So are the torques balanced in this case? Well, yes. How do I know they're balanced? Well, because it's in equilibrium. How do I know it's in equilibrium? Well, because it's not accelerating. So let's check the math. We know that there was a counterclockwise torque from big mg. That was 0.6 Newton meters. Well, in order to be balanced, I need to have a clockwise torque that's also equal to 0.6 Newton meters. Now, this force here, again, is not producing any torque. That force is not producing any torque because neither of them are offset, but this one here is. Now, what were the values? Well, we had them on the video. The value of this force was 2 newtons, and the distance from here to here was 0.3 meters. So this R times F would be 0.3 meters times 2 newtons, still the 0.6 Newton meters worth of torque. Now, last time we created this torque with an upward force. Now we're creating it with a downward force. How is that possible? How can an upward force do the same thing as a downward force? Well, it's not just the force, it's the force in relationship to that point of rotation. And the upward force on the left created a clockwise torque. The downward force on the right also created a clockwise torque. So I can use the same force, just in opposite directions on opposite sides to do the same thing. Now let's talk about the normal force. Last time, if you remember in our first example, our normal force was equal to our weight of the meter stick. It was equal to mg. That's because I had a down 2 newtons here, up 2 newtons here, and then these two were the two that had to balance each other out. Let's see how that works this time. It's in equilibrium. This meter stick doesn't have any angular acceleration. It also doesn't have any linear acceleration. So that means that my forces have to be balanced as well. So in this case, I actually have 3 forces acting down this time. So if my net force is going to be 0, I have big mg, I have mg of the meter stick, and then I have this new applied force. Those are all acting down. That's being balanced by my normal force in this case. So last time the normal force was just equal to little mg, but now the normal force is going to be equal to the 2 newtons from this, plus the 2 newtons from this, plus whatever mg is. So my normal force is actually going to be mg plus a little bit of extra. See, last time my up and down forces over here canceled each other out, so the normal force just had to pick up the slack. But now I've got a downward force here and a force here and this, so the normal force actually has to hold up all of these. Now, so far, I've only been using 2 Newton forces. I applied a 2 Newton force on the left, I applied a 2 Newton force on the right. So the real question is, do I have to use a 2 Newton force? Is that the only size force that can be used to balance this thing? I understand that this mass right here applied a 2 Newton force. So it makes sense that I could balance that out by using other 2 Newton forces. But is that the only force that's possible? Is that the only force that's useful in order to balance this? Well, no. You see, the important thing isn't that I'm balancing 2 newtons with 2 newtons. The important thing is that this has created a torque, 0.6 Newton meters, in the counterclockwise direction. So I'm not really trying to balance out the 2 newtons. What I'm trying to do is balance out the 0.6 Newton meters worth of torque. I'm trying to stop that rotation. So if I apply with our method 2, I've got it in blue here. If I apply this 2 Newton force at a distance of 0.3 meters, well then yeah, that gives me the torque needed to balance that. But it doesn't have to be 2 newtons. If I apply it at that location, it has to be 2 newtons. But what if I applied at other locations? So what I want you to do is I want you to try and decide what's going to happen, make a prediction, what's going to happen to the force required if I move closer to this fulcrum. I'll give you a minute to make a prediction. What's going to happen to the force required if I move closer to this fulcrum? Well, let's find out. Here I've got it balanced. This is still what we had with method 2. So method 2 is still going to be balanced. But now I'm going to take this force sensor right here, and I'm going to move it closer towards the fulcrum, this way. Now remember, it's not the 2 newtons that I'm trying to balance out. It's the 0.6 Newton meters of torque. It's that rotation that I'm trying to stop. So right now, this is creating just enough torque to balance out the torque from this one here. So if I move this closer, remember our equation for torque? Torque is equal to RF times sine theta if needed. Well, what am I about to change? I still need the same torque. I still need to balance out the torque from this one over here. But what I'm about to change is I'm about to change R. Which way am I going to change that? Well, by moving closer to the fulcrum, I'm actually going to decrease my R value. And in order to keep tau constant, while R decreases, what do I have to do? Just mathematically, what do I have to do with F? Well, F has to increase. Okay, we say that R and F are inversely proportional. So if I'm keeping torque the same, any change that I make to R, F is going to give me the inverse change. So if I divide R by 2, then I'm going to multiply F by 2. Okay, so any decrease, we can watch. Hopefully this won't fall on me. Just keep an eye on the force reading right here as I move this just a little bit closer. You can see that the force is gradually going up. Now the meter stick is still in equilibrium, it's not accelerating, but that force is gradually going up. Go ahead and stop it. Right about here. Right here, this is a new R value. My R value is now 0.2. Remember how much torque I need to create to balance this? I need to create 0.6 Newton meters of torque to balance this. Well, do we have it? Here I've got an R value of 0.2 and a force of about 3. So the torque over here is still about 0.6. That's why it's still balanced. Let's see what happens if I go a little closer. You can see the closer and closer I get, this force is going to get bigger and bigger and bigger in order to hold this thing in place. Okay, get a little closer, I'm gonna fall. Now, what happens if I would have brought this force outside of my original point? Well, outside of my original point, if I move away from it, I'm increasing R. So now I don't need F to be nearly as big. And you can see now I'm actually able to balance this. Whoops, off the screen. Coming back. Coming back. There we go. You can see now instead of using a full 2 newtons, I only have to use 1.8 or 1.7, 1.6, so on and so forth. The further away I get from that pivot point, the bigger this R value becomes, then the smaller and smaller the force needs to be to generate that torque. That's why we push, when we open a door, we push towards the outside of the door. We don't push it in at the hinges where the R value is real small. That's why if we're trying to loosen a bolt and we use a wrench, we use a wrench with a long handle, because if we just tried to twist it right at the bolt, we'd have a really small R value. But if we apply a handle, or if we use a handle, then we can increase that R value, and our same force can actually generate more torque for us. Or in this case, we can even use a smaller force to create that amount of torque. So let's take a look at another example. I'm going to go back to my original setup. Without the force being applied, I'm going to remove my force sensor. If you hear the commotion here, I want you to think outside the box a little bit. Of course, I can apply forces in different places. Forces in different places will give me torques. But I want you to think outside the box. Is there a way that I can balance this right now without adding any additional forces? I'll let you look at the setup. Can I balance this in a horizontal position without actually applying any extra forces? Watch this. There's no extra forces. My force sensor's sitting there, but it's not touching anything. What if I move this fulcrum a little bit? To a point kind of like this. Is this in equilibrium? Look, this is not touching, it's just sitting there. Is this in equilibrium? Yeah, because there's no acceleration, not linear acceleration or angular acceleration. It's in equilibrium. That means the forces are balanced and so are the torques. So how does this work? Well, let's draw one final free body diagram. One final setup. Go ahead and draw this meter stick one final time, but this time we need to make an important change. This time, our fulcrum is in a different spot. So it's going to look like this. So go ahead and draw your meter stick, just a quick little rectangle. You can go ahead and put big MG right here. I still know that. That's still my 2 newtons, right? That's my 2 newtons. I've got the normal force of my fulcrum is right here. Now you'll notice in this particular case, is this R value the same as it was before? Last time this R value was 0.3. That's not the R value anymore, is it? Let me switch over and let's see what that R value is. The R value here, if we look, let's see if I can mark this. Come on. R value here, got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 centimeters, so 0.11 meters. That's my R value now. So this little guy is not creating as much torque as it did before. So we'll go back over to here. The torque from this one is now no longer an R value of 0.3. Instead, it's an R value of 0.11 times still the same force, 2 newtons. So this is actually going to be a torque of 0.22 Newton meters. This is still going to be counterclockwise. Now the system's in equilibrium, so how is that possible? Well, in order to be in equilibrium, all my torques have to be balanced. I've got the normal force of my fulcrum right here. Is that contributing any torque? No, because that's at an R value of 0. That's right at the point of rotation. I can't make it rotate by pushing right at the point of rotation. But what other force is present? Yeah, the weight of the meter stick, right? So the weight of the meter stick, we can assess that at its center of mass. That's the weight of our meter stick. So that's actually creating, if we look, that's actually creating the the clockwise torque that we need. So the clockwise torque from my meter stick is actually going to have to balance out that counterclockwise torque from mg. So clockwise torque from the meter stick, that's going to be, let's look at it, R times F. What's the R value? Switching back, that was at 31, meter stick 50. So that's going to be 19. That's going to be 19 centimeters, so 0.19 meters. And the force, well, that's just mg of the meter stick. We haven't known that up until this point. But now we can actually figure that out. Because if this is the torque in the counterclockwise, then this has to equal 0.22 in the clockwise direction. So 0.22 divided by 0.19 actually gives me mg of the meter stick. 1.158, we'll call that 1.16 newtons. So now we actually found something we didn't know before. We actually found the weight of this meter stick. Now, how could we test that? Pretty easy. Take this little apparatus off. Get this off. I've got a force sensor just sitting here waiting to be used. So bring it into frame. Let's just hang our little meter stick off of this. Get you balanced out here. And we got 1.13-ish newtons. So we're within a couple hundredths of a newton. So I'd say we're pretty much dead on, which is what we would hope because we're using physics and physics doesn't lie. So we actually found something that we didn't know before. Pretty interesting. So just to kind of summarize today, we said that a torque is created by applying a force at some distance away from a point of rotation. We've got to have that force offset from that point of rotation. Torque will either create a clockwise or a counterclockwise. So we're less focused about is the force up or down and more focused about does it create a clockwise or a counterclockwise rotation? Because remember, an upward force on one side can create the same torque as a downward force on the other. In order to reach equilibrium, these torques have to be balanced. I'm going to put a problem up here on the screen. I'm just going to leave this for a few seconds. I don't expect you to write this down, but if you're on a computer, you can go ahead and hit print screen. You can save this image. If you are on your cell phone, just take a screenshot. You can save this image. I know yesterday some people were wondering if there was an image of the homework problem, so to speak. This is just a practice problem that Greg can go over in the beginning of his lesson tomorrow. But here we've got no fulcrum. I've taken the fulcrum out of this. Now we just have two students holding up on this meter stick, one on one side, one on the other. I want to see if you can explain why student B needs to apply a tension at all. See if you can explain what or determine a value for T2 in terms of mg. Describe any changes to this second tension as student B gradually moves closer and closer to the meter stick. So as they hold this closer and closer to the center. And then while that's going on, are there any changes that student A experiences? Do they notice anything different about their T1? So again, take a minute at some point this afternoon, this evening, maybe tomorrow. Feel free to see if you can work through this problem, see if you can navigate through it. If you have any questions about it, you can certainly hit me up on Twitter. You can also hit up Greg at Jacobs Physics, and either one of us can help you out, but I think he's going to start class tomorrow with one of these. So hopefully we'll see you guys back tomorrow at noon. I know we ran into a few issues today. If you want to just go ahead and subscribe to this particular channel, then it should let you know once we're live, but it should be right around noon every day. So look, I appreciate you guys. We're here to help. We're here to hopefully make this process a little bit smoother for you. So Like I said, Greg and I are looking forward to working with you guys over the next couple weeks. All right, thanks for watching, and we will see you guys tomorrow.